Right. Thank you, NSEC, for having me. Anyone that's here for their first NSEC? Me? All right, we got a couple. Awesome. Good on you. So welcome. I'm Mike Saunders. We're going to talk about intro to AV and EDR Evasion. If you want a copy of the slides, this talk is part of a larger talk that I've given, and this link here has all of the slides, including some of the stuff that I'm not going to talk about today. If you have questions afterwards, I'm Mike at redsiege.com. I'm Hardwater Hacker on Twitter. I'm on LinkedIn. Feel free to get a hold of me. Be happy to answer questions. A little bit about me. Flo told you most of the important stuff. I'm the principal consultant at Red Siege. I've been around a bit. Sadly, my InfoSec Twitter these days is mainly pictures of things that I do not InfoSec, but I'm into photography. I do a lot of fishing and kayaking and stuff like that. But enough about me. Let's get to what you're here for. With a disclaimer, I want to tell you that this talk is not about advanced evasion topics. We're not going to be talking about unhooking, and we're not going to be talking about evading runtime checks for the most part. So we're talking about ways that you can use to obfuscate your payload to get it to land on disk or to get it into memory. That's the intro part. The advanced talk is when we talk about the techniques we need to use to load that code into memory, to execute that code and stay hidden. So as I said, this is part of a larger talk where we talk about more things that get us caught, and some of the things we can do about that. And one of the things that can get you caught is entropy. And I promise you we will define what entropy is and what that means. Now, this is normally where I give you a whole bunch of other content before this point. But now we're going to hop right into entropy. So with regard to entropy, I do want to give you a disclaimer. I am not a mathematician, so I may not be explaining all of these concepts correctly. I'm going to do my best, but I am not a mathematician. I will tell you that we are talking about entropy as it relates to information theory, not the heat death of the universe. They're related, but we're talking about information theory specifically here. In addition to entropy, I'm going to talk about a concept called Kolmogorov complexity. So let's get into it. A rough definition of entropy is a measure of the amount of randomness in a given thing that you're observing. If something is said to be higher in entropy, it means that it is more random. If something is lower in entropy, it is less random. Now, I also mentioned Kolmogorov complexity. So Kolmogorov complexity comes from this theory that data that is highly random is less compressible than data that is less random. So we can test this. You can see on the screenshot, I did a simple little test. I read in 1 million bytes from dev urandom. So if I have a suitably random number generator, and I read in 1 million bytes, and then I'm going to compress that with gzip. Yes, I know you can use ent, and there's another bunch of tools that you can use to measure entropy, but gzip stands in as a good proxy, and it's available on all systems where ent isn't there by default. If we pipe in 1 million bytes of random data into gzip and we try to compress it, it tells us that it compressed it by 0.0%, meaning it did not reduce the size of the input at all. Because of Kolmogorov complexity, we know that that must be highly random data because we couldn't compress it. So we've got highly random data, which is high in entropy, and we can't compress it. So here's where the problem comes in. We typically use some means of obfuscating our shellcode, usually encryption. And when we use encryption, it increases the amount of entropy in our payload. Some AVs and EDRs will use a measure of entropy as a proxy for trustworthiness in a payload. And so we're going to take a look at that. But I want to take a little diversion. If this was the longer version of the talk that I've given before, I would tell you about some of the things that we get that get us caught. And one of those things is not changing default values. So if you've ever heard of the MS build technique and you've used MS build to get payload execution, you've probably heard of the 3G student template. And the 3G student template is a good template that a lot of people use, but it's very well known. It starts out with a task name, and this is an XML file that gets loaded by MS build if you're not familiar with the concept. It's got a task name, class example. It can be anything, but the 3G student uses class example. There's one default. We also have several things. We need to allocate memory and copy our shellcode into that. And it creates a variable called funcadder. Also helpfully has a variable containing our shellcode called shellcode. These three on their own might not be suspicious. But in the context of an XML file being loaded by MS build, that may be suspicious. So not changing these variables could be something that gets you detected. So you're like, all right, let's just use some random value for that. We'll just put that in. Well, that is also a problem. Because we put in random values, if they're truly random, they're going to be high in entropy. So we actually have these short variable names, but they're high in entropy. And if we replace variable and function names with random strings, that could be bad. I have been busted by EDRs that looked at my MS build template and said there's a high amount of entropy in the function and variable names. As a result, we think that this is untrustworthy. Just the randomness of the variable names was what it used to detect it because there was high entropy in there. So again, that high entropy is a sign that we're trying to hide something. A lot of times it means we've encrypted it. We're otherwise using random things to hide what we're doing, and that can cause a problem. So instead of using random strings, I use just custom word lists. But I don't use just a single word because depending on the language that you're developing in, you might run into reserved word collisions. It's especially common in like VBA. There's like all kinds of reserved words. But depending on the language that you're in, those reserved words could cause a problem if that shows up in your variable name because it's a reserved word. It means something specific to that language. So we use a random word pair generator. So splendid dragon or obfuscated diamond, whatever. NSEC, we could use that. But we have multiple words concatenated together. We do not have an entropy problem because we're not using random data. And we greatly reduce the possibility that we're going to have a collision in the namespace. So that works for things like scripts that we're using, scripts and code templates like the MS build template and other XML or JSON formatted or whatever type of template data. But let's get back to talking about compiled code. So we know that languages are not random. And while this actually could probably apply to computer languages, programming languages as well, I'm specifically referring here to like written and spoken languages that humans use to communicate. So I've done a little test. This first one, dictionary.txt, because you know I'm a heathen American and I assume that everyone speaks English, so dictionary just means English. And I tried to compress it with gzip, and I reduced it by 64.7%. It's a good amount. Compressed it quite a bit, which tells me that it's probably not very random. But now I did the same thing with the German dictionary, and I compressed it by 75.9%. So that tells me that, one, German is not only more terrifying than English, but it is also less random than English. It is more compressible. It is lower in entropy. So this leads to an interesting thought experiment that some people went down. You can check out these papers to find out more about it. But what they actually did is they took written language, like you can take Shakespeare, and then put in a Shakespeare sonnet, and that is your shellcode. And the position of characters within the words that go back to an algorithm that you have map to your shellcode bytes. It's a really smart paper. The guys that wrote this are wicked smart. I'm not that smart, so I didn't implement this, but I encourage you to read this and check it out. So, because I forgot to start my timer. There we go. All right. So why am I telling you about this? As with most stories that I share, they're related to things that I experienced on a test. So a little over a year ago, I was on a test. Client had CrowdStrike on their endpoint. And CrowdStrike had its next generation machine learning AV component enabled. So while it sounds like buzzword bingo, it actually did its job. I took a payload. It's the same payload I've been using for a long time. It's a shellcode loader, written in C, has some XOR encryption or AES encryption, I guess in this case I was using AES, and dumped it on disk, and I tried to execute it. And it didn't run. And I don't mean that it ran and it got terminated. It just didn't run. I double-clicked on it, nothing happened. Went to the command line, typed in the path, nothing happened. So I need to start debugging this. So I do it with a bunch of printf statements because that's how you debug things. And so the very first thing when this program starts up, it's supposed to say, hey, I entered main. But nothing prints when I run it. I put the new version on the disk. So that tells me it didn't run and get terminated. It didn't load at all. So why didn't it run? So I hopped on the Bloodhound Slack, the Red Team channel. If none of you are there, I encourage you to go check it out. It's a great place to learn from other people. And I was on there talking with some people, and we kind of all came to the same conclusion that it must be entropy related. It must be entropy that's causing this. So how can we defeat entropy? And defeat entropy checks, I should say. And of course, the entropy was high because I was using encrypted shellcode. So I've got this tiny shellcode loader that does not have many lines of code in it. And all it does is takes encrypted shellcode, decrypts it, sticks it in memory, and executes it. So there's not a lot of code there. And there's a high amount of encrypted data in relation to a small amount of code. So the entropy in the shellcode loader is very high. And CrowdStrike looked at that and said, I don't know what this is, but I don't trust it. I'm not going to allow it to run. Interestingly enough, it did not generate any alerts. My clients looked at it. They did not see any alerts, but it would not allow it to run. So there are a bunch of different ways that you can lower the entropy without actually recompiling your payload. You can just cat a bunch of non-random, non-binary data onto the end of a payload. You could cat, it doesn't work with a JPEG, right? It's got to be a PNG, I think. You could cat.png and redirect it to the end of a payload, and it would actually work. What I did is I compiled an array that contained a bunch of words into the payload, recompiled it, and dropped it on disk, and it worked. And this was my face, like literally what's happening. So this is what it looked like. This is literally what I compiled into my code. I created an array called anti-entropy, filled it with a bunch of words. 7,740 words there's no significance to that number. The only significance to that is that's how many words were in the dictionary that I had. Now, diversion back to another part of this talk, talking about compiler optimization. When you're compiling your payloads, you have the compiler that helpfully tries to optimize your payload for you. So it will try to take your program and make it use less RAM. It'll try to make it run more efficient because it looks at your code path and says, hey, here's some stuff that you never actually getting called. We're going to remove that from there. That can lead to a problem. We were using the shellcode loader, using it for years, that used a just XOR routine to obfuscate our payload, but we're using it with a multi-byte key. So like, an 8-word or 8-character long word was our key. And that worked for quite a long time until someday Defender started tagging on it. Like, what is going on? And again, because I'm an excellent programmer, my way of debugging it was removing chunks of the code. And I kept removing chunks of the code until the only thing left was this XOR routine, and Defender was still alerting on it. So that tells me it's looking at this XOR routine with a multi-byte key, and this is suspicious. Use it with a single key, just like a single character, like an A. It was like, this is fine. But using multi-byte key, it says, hey, that's suspicious. So the way we got around that, a coworker said, well, maybe it's compiler optimization. I was like, that can't possibly be. I did more tests, and then I was like, that's the only thing it can be. So I recompiled it, and I disabled compiler optimization. And sure enough, I now have my XOR routine is not compiled down to this highly optimized piece of signatured code, and now it works. So when you're compiling your payloads, it may be worth to disable compiler optimization. And I mention that because with a lot of compilers, if you throw this array in here, and I don't use it, I don't do anything. All I'm doing is compiling this payload with these words in there. Compiler optimization would optimize that out because it's not used anywhere. So I had to disable compiler optimization. So let's take a look at what that looked like. We have on the top my original payload, AES.exe. I can compress it by 18.4%. Now, because of Kolmogorov complexity, 18.4% we know is not a lot of compression, so it probably tells us it's very high in entropy. We take that same payload, the only thing that I've done is compiled in an array of words, and I compress it by 97.8%. Again, Kolmogorov complexity, we know that this is very not random data. We have driven down the entropy simply by compiling in these words into the payload. Now, it's not ideal because you can see that the size of my original payload is 362K. The size of this payload is 15 megs. Now, you know, a few years ago, Red Teamers, we were obsessed with the smallest payload we could have to get on disk. But these days, that, you know, internet speeds pretty fast. Everyone can download stuff real fast. So they don't really notice the difference between downloading 300K and 300 meg payload most of the time. So not obsessed with being as efficient as possible. I'd like to take another diversion though. And if you haven't heard about this, back in 2019, a couple of researchers were doing some research with Cylance's next-gen machine learning AV component. And as a tip for you, if you want to try testing against whatever vendor's new AV EDR component, but you can't afford the commercial business version, a lot of times the same engine is in their home product. It just doesn't have as good of reporting capabilities or as configurable. So that's what these guys did. They used Cylance's engine, but they bought the home version and they installed it. And so that was significantly less expensive. And they did some research, and while not related to entropy, it was an interesting study. They found that in their analysis, they found this database of words that Cylance seemed to be using as a test. If your payload contains these words, it gets a boost in confidence score. If it contains multiple words, it gets more boost. Well, it turns out there was some very popular game at the time that was getting blocked by Cylance. So Cylance's approach was to take all of the strings in this program and add them to their database and increases the confidence score. If these strings exist, this must be this game, it's good to go. So they figured this out, and they took the top 500 malware samples at the time, shotgunned these strings onto the end of the malware samples and ran them, and all of them passed. Pretty much all of them passed. So not related to entropy, but again, a very interesting research avenue that I encourage you to check this out. Another thing that we do, not necessarily related to entropy, is increasing the file size. Some EDR and AV engines, if you make the payload too big, if the file is too big, they will opt to not scan it because there's a performance hit by scanning large files. And so there's a trade-off between usability and speed, and they decide that people want things to be fast. So we are going to make it some threshold. If it's above 200 megs. I tried to find if there was a standard, but there's really not. It varies by vendor, and in many cases it's configurable, so people may have changed the defaults. I can tell you that Defender doesn't do it by default. By default, it doesn't care how big it is. But you can make a file large enough that the AV engine says, this is too expensive for me to inspect. I'm going to allow it to work. I promise you I am not picking on CrowdStrike here. I just happen to know it works against CrowdStrike because we did it recently. And the reason I'm bringing this up is because there are tools out there, like Optiv has Mangle, which is a great tool, but Mangle pads the payload, I believe, with null bytes. Other inflators will pad with random data. And some engines will look at files to see if they've been padded to increase the size. And if they're padded with null bytes or random data, that sometimes is a signature. So to avoid that, I came up with DigDug. Throwback to if anyone knows the reference between DigDug and inflating the side of your payload. Anyone? Right? All right, thank you for making me feel not old. So DigDug does the same thing that Mangle does with regard to inflating the size of a file. It artificially increases the size of a payload. However, I have set it up to read data from a dictionary. So you have a dictionary full of a bunch of words and then append those words onto your payload until it gets to the size that you specify. Now the entropy is lower, so we don't have an entropy problem. And it's big enough that the engine might opt to not scan it anyways. So you can check it out. It is on my GitHub, hardwaterhacker/DigDug. So let's get into a little more Evasion. I'm going to tell you about a tool that I created called Jargon. Jargon is special words or terms that have special meaning to a group. So us hackers have our jargon that other people don't understand. Popping shells doesn't mean anything to people who aren't a hacker. So after I did the CrowdStrike bypass, essentially by compiling in those words, I started thinking about it. Like, that was a really big payload, and I still had a payload that had shellcode in it. What if I could have a shellcode loader that didn't use shellcode? And what if I could, if it didn't have shellcode in it, I wouldn't have this entropy problem. So how can I decrease the entropy of my shellcode loader and also get code execution? Well, I know that English words, any language actually, will be lowering my entropy. So if I could encode shellcode as words, I would decrease my entropy and I would avoid having any shellcode in my payload altogether. So how does that work? I kind of came to this breakthrough, and I will add the disclaimer that I am not the person that invented this technique. Other people have done this before me. I have found other people doing it since I wrote this tool. I just haven't found anyone that had released it publicly in this form. So I don't want to state that I am the creator of this. I'm just the first tool author that released it, as far as I can tell publicly. So we typically store our shellcode in hex bytes, right? 0x00. But depending on how we declare our character array, we can actually store it as an int. We can store it as a 0, 0, 1, 2, 3, so on and so forth. Now, how many possible shellcode values are there? 256 possible values. That's it. No matter how much shellcode we have, it is always going to be made up of a maximum of 256 characters from that character set. So if we take 256 random words, and they have to be 256 unique words, and we put them into an array, and the position of each word in the array represents its shellcode value. So here, attending is a 0. Promptly is 1. Terry is 2, so on and so forth. So we get 256 words, we put them into a character array. Now each word in this array represents a shellcode character. And it doesn't have to be English words. We could take all the strings from kernel 32, for instance. That would be fun for an analyst to look at that and be like, what is going on with this payload? Right? So it could be any kind of thing, but we have 256 unique words. So we have a translation table. And as we said, 0 is attending, 1 promptly, so on and so forth. Now we do a lookup. We look at each of our shellcode bytes and we say, what is the value? Okay, that is a 27. We look then what is in the 27th position in our array. Yes, I realize 0 numbering, that's not actually true. We gotta offset for that, but just go with it. We look at what's in the 27th position of the array, we grab that word, and we insert it into our translated shellcode array. So this is our payload. In this case, it happens to be a Cobalt Strike beacon that I've encoded. And it's gigantic. Yes, it is gigantic, but we have a bunch of words in this array. And then when we want to go use it, our loader needs to contain the translation table, the translated shellcode, and a simple for loop. We loop through every byte of our translated shellcode table. And then for every byte, we look up the word in the translation table. Oh, that's at position 0, enter a 0. Oh, that's at position 256, put 255 into our shellcode array. Once we've done that, we've now recreated our shellcode and loaded it into memory and execute it. And it works. So if we take a look at this, again, our original loader was 362K. This one is 1.7 megs, so it's 10% of the size of the other one that we did. It's not quite as low in entropy. It's 85.8% versus 97 point whatever the other one was. But it's still much better than the loader containing our encrypted shellcode. So it's much lower in entropy. It doesn't actually contain any shellcode, to someone analyzing it. It's just going to contain a bunch of words. Does it work? Let's double click our payload. Receive beacon. So it does work. I've used this with C loaders, C++, C#, more recently in some Rust loaders. By the way, if you're not writing payloads in Rust, give it a shot. However, don't use things like AES or ARC4 or DES for your encryption routines, because the mere fact of loading one of those crates with Rust to some EDRs is a signal of badness. You can write a skeleton shellcode loader that doesn't have any shellcode in it and doesn't actually do anything, but it just imports the AES crate, and Defender's like, no, go away. I don't know what you are, but you're using AES, so it's bad. Jargon works great, though. So you could rewrite your own AES crate, that's fine, but Jargon works great with Rust. And I have a Rust loader that uses Jargon and doesn't do any unhooking, doesn't do any other evasion, and it works against several EDRs. Like, Rust is really a red teamer's fun language for a bit, right? That's going to catch up, but it is there. So if you want to try Jargon, you can get it on my GitHub, hardwaterhacker/Jargon. I encourage you to check it out. I encourage you to use it in your own tools. If you use shellcode pack from Ballast Kit, they've implemented that in there. If you can implement it, great. Have fun. Few other things. As I mentioned, I'm not the only person to come up with this technique, and other people have come up with really cool, similar ideas. If you were at DEF CON last year, there was a hack or a talk where someone used emojis instead of words. They used emojis for their shellcode, and it works, and that would be a fun payload to analyze. So shellcode is emojis. Check it out. I'm here to tell you that Cobalt Strike is not dead if you know how to use the artifact kit. Yes, there's a lot of signatures out there, but you can get around a lot of detections if you modify what's now known as the Arsenal kit, which includes the artifact kit. So definitely make use of it. Couple other things. I am not sponsored by these guys at all, but I think that the Sector 7 malware dev courses are a great intro if you're not super familiar with evasion and evasive coding techniques. Makes it very accessible. I would highly encourage you to check it out. It's like $250 per course, self-paced. Very much worth it. So with that, I think I'm right at the end of my time slot here. So are there any questions that I can answer for you?
Do a couple of questions. Oh, I think we have something. I think this is someone asking in the wrong room. So never mind.
Well, I won't answer that then.
Yeah, let's not do that.
Yeah, there's a question.
Yay.
Sure. So the question was, how complex will it be for AV and EDR to be able to detect these kinds of techniques? And that honestly is something I struggled with a little bit because I come from a blue team background. I am a blue teamer at heart, and everything I do is for the purpose of making the blue team better. Like, I don't care if I win. The only thing that matters is that the blue team is better at the end of the engagement. With this, I honestly don't know how you would detect it offhand. What I will tell you is the only benefit this gives you is bypassing that entropy check and that simple looking for shellcode bytes that are in there. You still have to do everything else to execute that code in an OPSEC safe manner. So there's still plenty of means to get caught. Like, the only thing that I can think of as a means to detect it is you have to go back to some real cryptography roots and do like character frequency analysis. Like, if attending shows up a bunch of times, well, we know that's the null byte or that's the 0. Like, okay, that shows up a bunch, and start doing frequency analysis. That would be a way of doing it, but I don't see that being an efficient way for EDR to handle it. Other than that, I'm not sure how they would detect it. You're welcome.
Got time for one more, maybe?
Yes, in the back. Would I recommend a sandbox to test in as a red teamer? Yeah, absolutely. If you have access to like some type of malware sandbox to analyze your payloads, it's both good and bad. I think that some of the roll your own ones that you can control the telemetry that's being sent would be better, because if you're using one of the more commercial sandboxes, they're collecting telemetry on your payload. And yes, it might not be detected right now, but I'm sure that they have a lot of your signatures, so it's going to show up eventually. So it's kind of more like if you can roll your own kind of sandbox where you can control what telemetry is being received, then yeah. But you absolutely need to analyze your payloads before you dump them on the customer environment, because there's a lot of failure. There's a lot of pain before the wins happen. So thank you. If you want to find me, I'm in the Red Siege shirt and the Red Siege hat. I'll be around the conference for a bit this afternoon to be happy to talk more. Otherwise, Hardwater Hacker on Twitter, Hardwater Hacker on GitHub, Mike at redsiege.com. Feel free to reach out.